Hi, I'm Miss Hearn. Let's get started. If we take this region and rotate it around the x-axis, we get this kind of odd shape here. And so when we rotate this, imagine that representative rectangle is just a disk, a slice of that, right? So if we could add up a whole bunch of those representative disks, then we would approximate the volume of this object. If we increase the number of disks, we get a more accurate approximation. And if we take a limit to infinity, we get exactly the volume of the disk. Since we know that the volume of this disk is pi r squared times the width, which is delta x, then we're going to be doing a summation, right? What does this turn into as an integral when n goes to infinity? The integral from a to b, pi times r of x squared, r of x is just this function here, gives you the height of the representative rectangle, times dx. We said that the formula for finding the volume was v equals pi times the integral from a to b of the radius function squared dx, or we could do this with respect to y as well, but we have to remember the key thing about the disk method. That representative rectangle, the rectangles we're adding up when we take that integral, has to be perpendicular to the axis of revolution. So you draw your function, you draw in the rectangle, the base of it is your dx or dy, depending on if it's the horizontal or vertical situation. And then you're going to figure out the radius by looking at the function of x or function of y that you have. Now we're going to switch it up just a teensy bit, because sometimes the area that you're revolving around the axis doesn't actually touch the axis, leaving a hole in the center of the volume, the solid of revolution. If you take a rectangle that doesn't quite touch the axis and you revolve that rectangle around the axis, it leaves a hole like a donut, right? It also looks like what's known in, if you go into Home Depot or whatever, as a washer, yeah? Okay, so they call it, this is called the washer method. It's really the disk method with a hole in it. You just subtract the two. So what we have is pi capital R squared here is the disk volume, the whole disk where it would have been if there weren't a hole. And then we're going to subtract the little disk that's missing from the center, the volume of the whole, pi little r squared w. You can actually factor out the pi and factor out the w. Pi times capital R squared minus little r squared times w. So when you actually see the formula for the integral written, v equals pi times the integral from a to b of the outer radius squared, think of it as the outer radius is capital R, and minus the inner radius squared. This is the shell method. So with the shell method, we imagine revolving a rectangle that is parallel to the axis of revolution. So this would be your representative rectangle here. This rectangle has a width w and height, if you will, h. And when you rotate that around an axis that it's parallel to, you get this kind of hollowed out cylinder, which we call a cylindrical shell. So it's the shell method. It's the shell of a cylinder, the outer part of the cylinder. In order to figure out the volume of this cylindrical shell, we need three dimensions. We need the width, we need the height, and then we need to know the radius to the middle of that rectangle. Draw a line right down the middle. This radius that goes from the axis of revolution to the middle of that rectangle we refer to as P. What we do is, how do we find the volume of a cylinder? Pi r squared times the height, right? The area of the base times the height. So the outer cylinder is pi times its radius squared times the height. The inner cylinder is pi times its radius squared times the height. We subtract them. It just simplifies really nicely. All you're left with is 2 pi times the average radius times the height times the thickness. For this method, if you have a solid rotating around the x-axis, it's going to turn out to be a dy problem. All right, so here's the formula. You're going to have 2 pi times the integral from c to d of p of y times h of y dy. P of y is this average radius, okay? H of y is the height. This is the gist of finding volumes of solids of revolution involving either the disk method, which basically is the washer method. Those are one and the same, and then shell method. What's the key? The key is drawing in your reference rectangle, and if you're using the washer method, it has to be what orientation? Perpendicular to the axis of revolution. Remember, washer method is disk method. Disk method, you're perpendicular to the axis of revolution. Wherever the base of the rectangle is facing, it's going to tell you whether you have a dy or dx. So for example, in this first diagram, since the base of it is facing the y-axis, this tells you you're doing a dy problem. If we're going to use the shell method, we want our representative rectangle to be parallel to the axis of revolution. So in this the third diagram, we have, again, the axis of revolution is the y-axis. If we want to use the shell method, we have to draw this reference rectangle or representative rectangle parallel to it. And notice that that gives us a dx in this case. The bottom of the rectangle is facing the x-axis. Over here, we have the x-axis is the axis of revolution, so we draw the rectangle parallel to it, and that gives us a dy. Why is this important? Well, first of all, if I tell you to use the disk method, you know you want your reference rectangle to be perpendicular to the axis of revolution. But also, if I don't tell you which method to use and you have to choose, sometimes it's easier to integrate with respect to y, and sometimes it's easier to integrate with respect to x, and you get to pick which method you want to use. Okay, so this reference rectangle idea is really going to be key to you deciding which method you're going to use. So disk method, perpendicular, shell method, parallel. You also need to know the formulas. I hope you found this video useful. If you did, please remember to like it. This method is featured in my next video. Follow the link.